Hello everyone, this is Vashishtha from Aerobase section. I'm going to explain about ducted fan noise, effect of duct inlet shake. So, inside the flow passages of a duct fan, what is a ducted fan noise? Inside the flow passages of a ducted fan, broadband noise is generated by a turbulent airflow. This type of noise can be suppressed by applying acoustic liners along the duct walls, and which will be described with the or reflecting the forward radiating noise back downstream by a stator inlet guide vane. So coming to the introduction part, noise produced by the environmental control system constitutes a significant part of overall noise inside a airplane cabin. So it has to be substantial impact on the passengers and crew comfort. Reliable prediction of a noise or revealing its main source and mechanisms are essential for designing better noise mitigating ECS. Of significant interest in this respect are various installations and interactions effects with particularly the effect of elevated level of turbulent fluctuations caused by non-uniformities of the flow in the ECS ducts or the noise generated by blower in ingesting such flow disorders. This effect is investigated exactly in the present study, which was carried out in the framework of a European Union funded project titled Integrated Design of Optimal Ventilation System of Low Cabin and Ramp Noise. So the nomenclature of a duct inlet contains the D duct diameter, frequency, FP, blade passing frequency, KT, the turbulent kinetic energy. M is equal to azimuthal number of duct acoustic node, and N is equal to radial number of duct acoustic node. P is equal to static pressure, P is equal to ambient pressure, PO is equal to pressure fluctuations, T is equal to time, U is equal to duct bulk velocity, U is equal to velocity scalar, with VR is equal to radial velocity component. So there are different types of ducts or CADs which can be AC fans, which can be seen in this figure, or different types of CAD models were considered AC fans. As you can see, this is an engine with the duct with the fans, and there is a duct. I mean, there's a covering in the covering for the wings. I mean, winglets, which reduces the noise. And as we can see in this flow with the 12 loudspeaker modules and system microphone modules, with ESA fan, with the turbine, with the bell mouth rectangular T-junction. Circular duct with fan module with different inlets and schematic representation for experimental mock-up used for the model extraction of the noise. So as you can see, the experimental rig for the various ducted fan test cases is installed in the anechoic room of a One Karma Institute for Fluid Dynamics. The duct is composed of modules corresponding to the fan or a various flow obstructions and instrumented sections. Static pressure probes, a radial and azimuthal hardware traversing system, microphone multiports, and loudspeaker arrays. The modules are made of acrylic glass as described in the introduction to create flow distortion upstream of the fan. The well-mouth inlet module shown is replaced by inlet modules with rectangular to circular transition and a T-junction. Geometry results in azimuthal inhomogeneity of a main flow and the turbulence intensity being ingested by the fan, causing an extraneous tonal and broadband noise generation. That system made of acrylic glass in the anechoic room with a bell mouth inlet. Here, due to the fact that the microphone arrays and loudspeaker modules must be located between the blower unit and the inflow module in order to extract the modal content of the acoustic source. The minimum distance between the blower inlet and the inlet module has to be larger than 4 duct diameters. As a result, the degree of main flow inhomogeneity that is ingested by the fan is noticeably attenuated with respect to what the same inlet geometry would generate for a short duct. So this is illustrated by figure 3, which shows cross planes just downstream of the inlet geometry and just upstream of a fan inlet, approximately 4 duct diameters downstream of the duct inlet for bell mouth inlet and rectangular to circular inlet and T-junction inlet. These are different types of inlets as we can see in this diagram. So, as you can see, this is the hot wire scanning grid, an example of measured axial velocity field. As you can see, these are the fans, ducted fans, with higher velocities at middle and lower velocities at the end of the fan. Here, as we can see in the middle of the coming to the computational methodology. In general, the approach developed for the solution of the considered problem consisted of a direct computation of the noise produced by the fan based on a compressible scale resolving simulation of turbulence with the use of a hybrid Ran's method of the detached eddy simulation type. Namely, the improved delayed detached eddy simulations. This method is currently well established for unsteady simulations in both aerodynamic and aeroacoustic applications, including engine and airframe noise. These are the structural diagrams with this eddy simulation with the precursor RANs of inlet and precursor URANs of fan flow and with the fan inlet module fan module and production of eddies. Fans are at their quietest when operating at peak efficiency, bend and damper close to the fan are common noise reduction features. Simple methods using 2 to 3 duct diameters of a straight duct between any feature that is disturbing the flow of a fan itself can cut down the noise by up to 12 dB. And coming to the computational domains and inflow and outflow of boundary conditions. The location of the inflow and outflow boundaries of the computational domains and boundary conditions used in these three stages of the fan flow computation outlined previously are presented. A precursor study RANS is performed in the computational domains, which include the inlet modules and adjacent part of the ventilation duct of the length of 5D at the RANS inflow boundary. The total pressure and the temperature are described. At the outflow, the static pressure is assumed to be a constant adjusted to the course of the computations to match the experimental mass flow rate. Through the duct equal to 0.636 kg per second for all three considered cases, the correspond to the bulk flow velocity 32 meter per second. The computational domains used in the precursor URAN stage are in the main production are identical and you include the fan module and upstream and downstream parts of the duct of length 3 and 60 respectively. Grid on the walls of upstream and downstream parts of fan casing and hubs and blades of surface grid and the grid meridian. These are the diagrams including all the different types of ducts and velocity differences given here. Results of simulations and comparisons with experiment. Instantaneous flow visualizations with the time, average speeds, and turbulence statistics. Baseline case of Belmont inlet ducts with IDDS versus Uranus prediction sample visualizations from the IDS of the flow are presented in the form of instantaneous fields of vorticity magnitude and streamwise velocity in the meridian plane of the duct combined with the fields on axisymmetric grid surface inside the passage between the hub and the fan case. As results shown here with the radius of the cylindrical part of the passage r sub 0.06 meter and r sub 0.07 meter and r sub 0.08 meter. Other than this, the 3D view of instantaneous vorticity and two 3D views of instantaneous isosurfaces of full magnitude are also given. And coming to the effect of duct inlet shape. The effect presents snapshots of the vorticity magnitude and the streamwise and radial velocities in the duct cross section upstream of the fan. Recall these fields are created by the VSTG based or corresponding RNS solution slightly upon the region of the figure reveals a significant differences in turbulence impinging of on the front surface of the hub and on the rotor blades for the three considered inlets. In the case of the clean Belmont inlet, only fine-grained turbulent structures confined with a narrow boundary layer on the duct were observed. With the T-junction inlet, the presence of large-scale turbulent structures upstream of the fan is evident, and the turbulence covers the whole duct cross-section for the inlet performed by the rectangular to circular transitions. These are the instantaneous peaks of vorticity magnitudes and streamwise and radial velocities upstream fans in duct with the three inlets, with a bell mouth, with a rectangular or circular mouth, and with a T-junction mouth. And the bell mouth, rectangular T-junction mouth with predicted effect of type of duct inlet 3D views of instantaneous field of vorticity magnitude, and with predicted effects of type of duct inlet on resolver T gauge meridian plane. A combined experimental numerical study of ducted fan was performed to present network demonstration the highest potential of hybrid and with except of low frequency noise propagating in the upstream direction which increases up to 10 dB. On the experiment side, definition of scattering and reflection matrices. It shows the high value of invoking techniques of model decomposition. So this is all about my explanation. Thank you.